Good morning to you all. I hope you had a great weekend. We're going to finish up our chapter on thermodynamics today, I think, and we're going to talk a little bit more about the things you can do with delta G. And delta G, or G, is called Gibbs free energy. And Gibbs was the scientist, he was an American chemist who created this idea for something vaguely based on the second law of thermodynamics. And in the second law of thermodynamics, any product-favored reaction, which is anything that happens, all right, you should have an increase in the entropy of the universe. And delta G is related to delta S of the universe. It's the opposite sign though. So while delta S of the universe is a positive number when something happens, your delta G will be a negative number. So everything you do, all right, from drinking your drink to writing with your pen and doing things on the computer or calculator or cell phone, all right, all of those things, something's happening, all right? And so all of those would have a negative delta G. So literally this delta G is super popular and powerful when it comes to the physical sciences, because if you don't have a negative delta G, then those reactions are going to be harder to get going. And we'll talk about some ways in the next section how to get around that. But for right now, just realize that delta G is really important. If the Gibbs free energy change is negative, your reaction is going to go. On the other hand, if you have a positive delta G, then the reaction will not be as likely to go. Now, there's actually several different methods for finding delta G. And the main one, the one we focused on a lot on Friday, was delta G equals delta H minus T delta S. And I babbled something about delta H and delta S being double sides of the snake, and they sometimes fight each other, and sometimes there to go. Station identification. Well, that wasn't supposed to happen. Wow, that wasn't supposed to happen. Hold on here real fast. We'll see what I can figure out what's going on. Another chalkboard lecture. Exactly right. It might come out to be that way. Okay, hold on. Talk about yourself for just a second. Let's try an alternate way that I had. That worked last time. We'll see if this works this time.
No, how are you? Just met with my mom yesterday. How about you?
Okay. Sometimes. All right, let's try that again. Sorry about the confusion there. That was unexpected. So anyway, two ways to find delta G. One way is through the combination of delta H and delta S values. And that's when sometimes delta H and delta S values are aligned and they work together, and sometimes they fight. So in this first case, you would find delta H of products minus delta H of reactants, and you would have a value. You'd then find the same thing for delta S. You'd have the entropy of the products minus the entropy of the reactants, and you'd have a value. and plug those in with the temperature, and you can calculate delta G that way. And again, like I said before, I was interrupted. Delta G, when it's negative, those are the reactions that are going to occur, and the positives ones won't. However, there's also another way, and we're actually going to see several ways, but these are two of the cool ways. You can also look at tables of delta G values. And the same table that has the delta H values and the delta S values, there will usually be a third column of delta G values. And if you have everything you need, then you can go delta G of products minus delta G of reactants, just like you did for the delta H and the delta S. And this is an alternate way. It's a little easier because you don't have to have all the delta H and delta S, but of course you have to have the delta G values. These are just a small sampling of values of delta G from a table. And you can see that most of the delta G's are negative, all right? If the delta G is negative for one of these compounds, that means that it's going to occur. So iron oxide, iron 3 oxide rust is definitely ready to go. It's got a very negative delta G, and that means it's easy to form. On the other hand, notice how diamond has a positive value. And diamonds, thermodynamically, really are not favored. And we've talked about this before. It takes forever for a diamond to decompose, but it will. So making a diamond is not thermodynamically favored, all right? You're going to have problems doing it, but there are, of course, ways to do it. Now, I'd also like you to see that all of these values here are 0. And these values are all elements in their standard states. And just like delta H values, if you have an element in its standard state, the delta G and the delta H values will be 0. So if you look at the periodic table, things like helium as a gas, and bromine as a liquid, and I don't know, zinc as a solid, all of those elements in their natural states would have delta G's of 0. All right, so you don't have to look them up. If you have like liquid helium, all right, or solid bromine, or zinc that had been heated up and turned into a liquid, then you'd have to look up the different values and stuff to see. But normally, if you have an element in its standard state, the delta G is 0 and the delta H is 0 as well. But the entropy, remember, will only be 0 if you're that perfect crystal at 0 Kelvin, which is like never. So you always have to look up entropy values, all right, always, and they should be positive numbers. But delta G is usually negative, 1 or 2 positives, and if you see something that's 0, it's just an element in their standard states. Okay. So here's an example of how you can calculate something like this. Let's say that you want the delta G for this reaction, and I have here the couple of values, carbon dioxide and diamond. So to figure out something like this, delta G would be products minus reactants, all right? So you take the delta G of CO2, this number, and you would subtract the delta G for diamond and the delta G for oxygen. But why did I not place the oxygen value up there? It's 0, that's right, it's an element in its standard states. So you just have a delta G of 0 for that one. So if you go through the math, and it's up to you if you want to, it comes out to be negative 397.3. Notice that even though diamond was positive, we do subtract it. It's products minus reactants, all right? So 394, and we subtract the 2.9 from it. Any questions on that? Here's just some more examples. Combusting carbon to CO2 is very, very product favored, all right, which means you get a negative delta G. And again, the problem we're having with greenhouse gases and stuff like that is that carbon is so ready to go to CO2, all right? It'll go to CO2 usually above everything else, and even intermediates like DNA and sugars and stuff like that will eventually go to CO2 as well. The delta G, again, of the elements are 0, product favored, too much product favored, greenhouse gases, global warming, etc., etc. Oh, well. Any questions on the process? Some reactions can be called enthalpy-driven or entropy-driven. So, like we had earlier, all right, delta G equals delta H minus T delta S. Now, this is like, you're like taking these two and you're adding them or subtracting them from each other, all right? And the goal is to get a negative delta G. So if delta H is negative and your delta S is positive, but you're multiplying it by the negative right there, then you have a negative term for delta H, and this whole thing becomes negative if delta S is positive, making delta G negative. So in my chemistry world, if you have an exothermic delta H, all right, if delta H is negative, that means that that reaction is enthalpy driven. Negative delta H's contribute to a negative delta G. So every time you see an exothermic reaction, those are enthalpy driven reactions. They want delta G to be negative, which means it's going to happen. You can also have entropy-driven reactions. Now, entropy values have to be positive to make delta G negative. It's kind of weird, like a positive here, but times a negative makes this whole thing negative. So if delta S is positive, those reactions are called entropy-driven. An entropy-driven reaction just makes delta G more negative. So if you have delta H and delta S working together to make delta G, you'll have both an enthalpy-driven and an entropy-driven reaction. Your delta H will be negative and your delta S will be positive. So keep on the lookout for the signs of delta H and delta S, all right? The negative delta H is enthalpy-driven. The positive delta S is entropy-driven, and that just means that those terms are going to try to make delta G more negative. Oh, of course my sound isn't working. Well, this has definitely been one of those days for the book. All right, hold on. Let me see if I can get this thing to... Okay, there's a problem with the sound, so you're just going to have to deal with it. I'm sorry. So this is going to be cheesy, but that's basically how I roll.
When we pour sodium carbonate into hypochloric acid, it dissolves rapidly to produce aqueous sodium chloride and gaseous carbon dioxide. In this case, entropy increases, and the reaction is energetically favored to occur. It is both enthalpy and entropy driven.
In this reaction, if you didn't know anything about it, what was happening, all right, you saw a lot of bubbling and energy and things like twirling around and stuff like that. That's where the enthalpy-driven part is, all right? Enthalpy is about energy. If you see a lot of stuff happening, that means that, man, this thing is enthalpy-driven. You could actually feel that the test tube was warmer after than before because all this energy would have been given off. But also notice how you saw a lot of bubbles in there. And the entropy of gases is always higher than the entropy of liquids and solids. So if you start seeing bubbles form, then you also can make a pretty strong prediction this is going to be entropy driven. So in this reaction, we saw something happening. Delta G is negative, all right? Highlight that. We saw something happening. Something happened. It didn't just sit there, all right? Your delta G is negative. Your delta G would be positive if we didn't see something happen. So we saw something happen. Delta G is negative. Lots of energy. Wow. You can feel it getting hot. That's enthalpy driven. That means delta H is going to be negative. And also, you saw a lot of gases form. And unless you start with gases, which this one certainly wasn't, that means almost for sure it's going to be entropy driven. Your delta S is going to be positive. So again, without knowing anything about what's happening, I can predict the signs of all three of these values, all right? I saw something happening, delta G negative. Lots of energy. Sound effects not necessary. Delta H negative, enthalpy driven. I also saw the gases form where there were no gases before. Delta S positive. This is enthalpy driven and entropy driven. If you calculated those values, delta H products minus delta H reactants, delta S products minus delta S reactants, they should correspond with these. And if you calculate delta G, then it should come out to be negative. Now, not all reactions are this way. So here's an example of something that's very common in society, which is using an acetylene torch for welding and stuff like that. And I burned my fingers on the stove, so I don't know anything about it. But anyway, this is a reaction which you've probably heard about and seen. The guys have people have the masks on and stuff like that. Acetylene, this is a combustion reaction, which is something we've talked about. Acetylene, this thing, reacts with some oxygen to make CO2 and water. Now, if you use the enthalpies of formation, i.e. figure out the delta H of products minus delta H of reactants, this is the number you get out. Now to get this number, I took 2 CO2 delta H and added it to a delta H of water, and then I subtracted delta H of C2H2 and the 5/2 O2. And when I did that, I got this number right here. Is this an enthalpy-driven reaction, yes or no? Yes, good. Delta H is negative, all right? Anytime your calculated delta H is negative, we would call this then an enthalpy-driven reaction. Enthalpy wants this reaction to go. Now you can do the same thing with delta S, all right? You figure out the entropies of the products, these 3 guys, and subtract the entropies of the reactants, those 2 right there. And when I calculated this number, I got a negative delta S. So is this reaction entropy driven? No, good. If delta S is a positive number, that's when we refer to it as entropy driven. This is not an entropy driven reaction. So what we have here is we have an enthalpy value that wants this reaction to occur, but we have an entropy value which really doesn't want this reaction to occur. Now, if people are out in the automotive section right now, where they're acetylene torches, sound effects not necessary, I know, but all right, and they're using them, do you think that delta G is going to be positive or negative? Negative, good. If you see something happening, the sparking of a torch or the burning of a gummy bear or whatever, that means your delta G is going to be negative. So at room temperature, if we throw this together, we had better get a negative delta G. Acetylene torches are used all over the place. My welding people, friends tell me. I don't know anything about it, but anyway, yeah, so this is a reaction which is going to go. Delta G is negative. But notice here is kind of a fight. All right, delta G is negative, it wants it to happen. Delta S negative doesn't want it to happen. This reaction is happening because of the enthalpy, so it's enthalpy driven. Okay, so this is the value of this thing. We can see that enthalpy is contributing towards the spontaneity, which just means that something's going to happen. Entropy, though, really doesn't want this to happen. It's you've got 3.5 moles of gas going to 3 moles. That's not very entropy favored. It would rather have more moles of gas than less moles. Cool. Questions? Okay. So let's go back to our ammonium nitrate example. An ammonium nitrate as a solid, when you place it in water, all right, it does dissolve. It's endothermic. It takes energy and stuff to happen. Now, if it takes energy to make the solid dissolve, what is the sign of delta H? Positive. Well done. If delta H is positive, that's when you have an endothermic reaction, and you can write heat as a reactant. If delta H is positive, is this an enthalpy-driven reaction? No. Delta H has to be negative in order to make delta G negative. This has a positive delta H. So this reaction is not enthalpy-driven. Now, earlier I stated that the solid does dissolve, making a solution, all right? Something's happening. What will be the sign of delta G? Negative, good. Positive delta G's mean that something's not going to happen, all right? It's the negative delta G's that we're after. Negative delta G is related to the positive delta S of the universe. So with these kind of things, they'll look for the negative delta G's. So if this happens, and it's not very exciting, but it does happen, all right? That means that your delta G number is going to be a negative number. Now, if delta G is negative, but delta H is positive, it's not enthalpy driven. What can we tell about the sign of delta S for this reaction? positive. You have to have either a positive delta S or a negative delta H, or maybe both even, to make this negative. But we saw here that this reaction is going to have a positive delta H. We must have a positive delta S here to make delta G negative. All right, that's the only way this reaction is going to go. So this reaction we're going to refer to as entropy driven. All right, enthalpy is not helping here. It actually wants energy from the outside. It's taking the outside energy and putting it in. Entropy here has to be positive.
In the center beaker is water at room temperature. To this we add solid ammonium nitrate. The ammonium nitrate dissolves. Usually, a reaction that occurs so readily is exothermic, but we see from the thermometer that this reaction is endothermic. The temperature of the water drops significantly. This reaction is not favored energetically, yet it still occurs.
So again, the drop in temperature means it's not enthalpy favored, it's endothermic. Endothermic reactions don't make reactions generally occur. So we must have an increase in the entropy, and you can calculate that. So just like before, here are the calculated values of delta H and delta S. So this first one, products minus reactants, ammonium nitrates delta H in the solution minus ammonium nitrate solid value. All right, you get this value, positive delta H, definitely endothermic. Takes energy to happen. So again, notice how I'm really focusing on the signs here. All right, signs will tell you a lot of things. This positive number again is endothermic. It needs energy, and it's not making this reaction happening. Enthalpy doesn't want this reaction to go. If you do the same thing though for entropy, you can take the entropy of dissolved ammonium nitrate and subtract the ammonium nitrate in the solid form. And that value does come out to be positive, all right, positive 108. Positive entropies make for spontaneous reactions. And again, spontaneous reaction just means that your reaction is going to occur. So this reaction is entropy favored. It is not enthalpy favored. So when you calculate the delta G at room temperature, which is where this was done, 298 Kelvin, you get a delta G of negative 6.7 kilojoules. And remember that negative delta G's are the values that are going to occur. This reaction is product favored. It's going to happen. Delta H not helping out at all, kind of being obstinate actually. Entropy is the one that's allowing this reaction to occur. So again, the positive delta S's mean entropy driven. The negative delta H's mean enthalpy driven. And the goal for a reaction, if you want it to occur, is to get a delta G which is negative. Notice again how delta S is usually in joules and delta H is usually in kilojoules. So when you combine them, make sure you convert one to the other. I usually go turn my delta S into kilojoules to make it go there, but you could go joules as well. Here's another reaction. Iron 3 oxide can react with a form of carbon to make pure iron and carbon dioxide. And let's say that Hunter and I look at this reaction like, yeah, making pure iron from basically rust? Score! That sounds like something worth a lot of money. Well, Hunter then does a little math, and he figures out the delta H and the delta S values, all right? And again, how you get these numbers, delta H of products minus delta H of reactants, that's where this number came from. And in the corresponding table of entropy values, entropy of products minus entropy of reactants, you get this number right here. And so if we figure out delta G at 298 Kelvin, which would be delta H minus 298 times this number in kilojoules, we get delta G positive 300.8 kilojoules. So looking at delta G, is this reaction going to occur or not going to occur? Not going to occur, all right? Positive delta G's are reactions that aren't likely to occur. They're reactant favored. So I look at these numbers and I'm like, oh, sorry, Hunter, I guess we're not going to make any money because delta G is positive. All right, cool. But Hunter's a pretty sharp guy, and he looks at these numbers a little bit more, and he goes, well, yeah, at 298, it's not going to happen. But is this reaction enthalpy, entropy driven, or both? Entropy. Entropy, this number right here, is something that says, I want this reaction to go. And entropy times the temperature, all right, is how we would figure out the contribution to delta G. What do you think is going to happen if we really raise the temperature a lot? Do you think this reaction would start to occur, or would it still not occur? Start to occur, right on, because temperature times delta S can begin to overpower delta H. What we have here is one of these classic, in my opinion, kind of double-headed snake things, all right? Entropy wants the reaction to occur, enthalpy does not. Positive delta H wants to occur, positive delta S, wants to occur, but positive delta H, it doesn't want to occur. So what we can do is figure out the temperature at which the delta G gets negative, i.e. when it becomes spontaneous. And if we raise this temperature high enough, that delta S term is going to overpower the delta H term. Now, how you can do this, all right, is we want to figure out what I consider to be the threshold temperature where delta G is no longer positive, but it's actually 0, all right? So if you let delta G equal 0, and that equals delta H minus T delta S, you want to solve for the temperature here. So if you rearrange this equation, at first it's delta H equals T delta S, and if you divide both sides by delta S, temperature equals delta H over delta S. This is the delta H value from before in kilojoules. Notice here we turn joules per Kelvin into kilojoules per Kelvin. We want those kilojoules to cancel out. And lo and behold, 835.1 Kelvin pops up. Now that temperature is going to be important to Hunter and I, because if we really want this reaction to go, all right, this is the temperature at which you go from having delta G's that are positive to delta G's that are negative. If this is worth it to Hunter and I, we can pump our reaction measure up to, say, like 900 Kelvin, all right? And that's a pretty serious temperature, but if the money's there, it might be worth it. We could figure out a way. At 900 Kelvin, this delta G will become negative, all right? Because at 900 K, that times this will be more powerful, if you will, than delta H. And at that temperature, your reaction becomes spontaneous. So if you have a reaction, and it's something that, it's so easy for you to have, you got all the raw materials, blah, 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 but you calculate a positive delta G, and then delta S is positive and delta H is positive, then you can play with this temperature, and there will be a temperature at which the reaction becomes spontaneous, at which it begins to occur. So, any questions on that? This system works awesome when delta H and delta S are the same sign, all right? Because if they're both the same sign, then that means that one of them, in this case entropy, wants the reaction to go, and delta H, the other one, doesn't want it to go. If they're both negative, then delta H would want it to go and delta S wouldn't. So as long as your temperature comes out to be a positive number, you're good to go. But what I have seen sometimes people do is they'll have like a negative delta H and a positive delta S, and they come out with a negative temperature. And if you get a negative temperature, then what that means is you don't need this threshold temperature, because you've either got a reaction which is always going to go or a reaction that won't go. So if you don't get a positive temperature here, that means that you've got to look at your delta H and delta S to see if you need the threshold temperature. Here's another example that's maybe a little bit more obvious, but ice going to liquid at freezing point of water, which is 0 Celsius or 273 Kelvin. There's literally like a threshold at 273 Kelvin, all right? Less than freezing, of course, you're more likely to have the ice. And greater than 273, you're more likely to have the liquid. So depending on the temperature, you're going to have a negative delta G above freezing for the ice going to liquid because it wants to occur. On the other hand, if you're really thinking about solid going to liquid, then down here your delta G would be positive. At temperatures less than 0 Celsius, you wouldn't expect the ice to go to liquid. Your delta G would be a positive value. So sometimes this maybe makes more sense than me getting excited about making some non-spontaneous reaction occur at different temperatures. This is a way you can actually see how these threshold temperatures work, all right? Above 0 Kelvin, or thanks for playing 0 Celsius, there we go, your delta G will be negative. On the other hand, less than that, then you wouldn't have anything happen. So, here's a reaction you might think about. You've got some kind of generic reaction. It's not product favored at room temperature. Stop right there. What is the sign of a delta G if it's not product favored? Positive. All right, so delta G is positive. At what temperature will the reaction become product favored? And here's values of delta H and delta S. So again, to find this, what you want to do is delta H initially equals T delta S. You're finding that threshold temperature. Delta H divided by delta S is what you want to do, but you also want to make sure you make the units the same. So here's kilojoules and there's joules. All right, so divide 50 by 0.1 or something like that. You should come up then with 500 Kelvin. So what this means then is that temperatures above this temperature, like 501, you would start to have a reaction which was product favored. Your delta G would be negative. But under this temperature, 499, or room temperature, which obviously is easier, you will have product favored values and stuff, and it won't work. Yeah.
So if 500 is the threshold, does that mean it's not actually going to happen at 500?
You're right.
Become product favored?
Totally. I would say you're right there, and you're not going to have a preference for either side. So you'd have like some product form, and they would go back to reactants while some of the reactants go.
If you set delta G to 1, that would be good.
Yeah, that would be fine. It's and this reaction up here, it's a lot easier mathematically if you just let this be 0. All right. If you set this equal to 1, then your math gets a little more complicated. Chemists are lazy. All right. So if you use this way, then temperatures above that will become product favored. Good. Questions on that? Last thing, delta G is related to equilibrium constants K, all right? And delta G, you can think about it as a way to convert delta G from K. So if K is greater than 1, that means you have, of course, a product favored. Just like we've seen, if K is less than 1, you're going to have a reactant favored. So delta G and K are both related to each other. And the last thing we're going to do here is just look at this equation, which is a way to relate the equilibrium constants K to a delta G. So this is actually now a third method to find delta G. If you have the equilibrium constant K, and that could be a Ka for acids, a Ksp for solubility, a Kp for gases, whatever, all right, plug it in there. Natural log, this is the gas constant, what I call the energy gas constant, 8.3145, and the Kelvin temperature. All of those things will allow you to find delta G. Delta G will come out in joules because of the R value we're using, so just realize that. Conversely, if you have a delta G for an equilibrium system and you want to find the K, you can use that delta G, make sure that delta G, which is usually in kilojoules, and the R value, which is usually in joules, make sure they have the same kind of units. Delta G divided by minus RT. You can take the anti-natural log. I'll show you an example. That's another way to find K. A lot of the KSP values, they actually use this method. They'll find the delta G for it first, and then they back calculate what the K value is. So here's an example of how this works. All right. Dinitrogen tetroxide is in equilibrium going to 2 nitrogen dioxides. And we've talked about this reaction in the very beginning of Chem 223. But anyway, the delta G for this reaction is positive, all right? And remember that positive delta Gs are the ones that don't usually occur. But if you wanted to calculate the equilibrium constant K, no problem. This delta G goes right up there, minus RT. We're going to solve for K. Now remember that you've got to make the kilojoules and the joules cancel out. So in this case what I did is I multiplied this number by 1,000 to get just the joules. So 4,800 joules equals minus 8.3145, the R value, times 298, natural log of K. So if you take all of that and you divide by RT, you get the natural log of K equals minus 1.94. And to get it into just K, you take that little E thing, the little anti-natural log, usually second function ln on your calculators. So E to the minus 1.94, it comes out to be 0.14. Is this K value product favored or reactant favored? Reactant, good, that's right. Ks that are less than 1 are usually the reactant favored. So like the small KSPs and the small Kas and KBs, those were all reactant favored systems. This is also reactant favored. Anytime K is less than 1, you're going to have reactant. So notice here that Ks less than 1 correspond with positive delta Gs, all right? A reactant favored reaction by equilibrium constant corresponds to a positive delta G, one reaction that won't go very well. So if you have a positive delta G, your calculated K should be less than 1, reactant favored in both cases. On the other hand, if you have a delta G which is less than 0, i.e. a negative delta G, one that's going to occur, then your equilibrium constant K should be larger than 1. They kind of go together. And again, you can kind of make sense of the numbers, make sure you're good to go. The only thing to pay attention to, that these aren't too hard, but the kilojoules to joules, sometimes people forget, so just make sure you use the same kind of units. Any questions on that? Cool. So here's an example of a reaction. We found the equilibrium constant to be 0.444. Let's calculate delta G. And oh, big surprise, left the equation up there, okay? Minus RT natural log of K. R, again, is a number I would like you to know, / memorize, / put in your calculators. 8.3145. We'll multiply it by the temperature, which is this number, 452.2. And we'll take the natural log of 0.444. And when you do this, you're going to get a pretty large number, and that number comes out to be a number in joules. So if you then divide by 1,000, you're going to get a number in kilojoules. And when you do this, when I did it, I had the 3.05 kilojoules per mole value. Again, you can check yourself on these. A K less than 1 is reactant favored, and Ks less than 1 correspond to delta Gs, which are positive. So it's only going to be A, B, or C. All right, it won't be D, and E is silly at this point. So you can kind of make sense of your numbers, make sure you're on target. Any questions? So this is kind of it for this chapter, and you're seeing here how scientists can use thermodynamics to make some pretty serious predictions about how things are going to run. But one thing that at first really made scientists sad, I guess, was that if you calculate a delta G which is positive, all right, those reactions are the thumbs down. Those are the reactions which aren't supposed to go. And at first it might seem like, oh, thermodynamics, man, we just aren't going to have that happen. Well, gosh darn it, all the people that studied electricity actually gave thermochemists and thermoscientists a really awesome way to make reactant-favored conditions happen, all right? And it's involved in the transferring of electrons from one thing to the other. And in science and chemistry, this is usually referred to as electrochemistry. And electrochemistry just means that you're adding essentially electricity or the study of electricity to make reactions occur. And in our own lab, we've used the products of a lot of electrochemistry reactions in the chemicals. So like if you've ever seen me use like pure sodium metal or they have like tanks of chlorine gas and stuff like that. A lot of the pure elements couldn't be made without electrochemistry, without knowing it. But on a more personal level, all right, you can see up here from this picture, all of us use batteries all the time, all right? Our watches, our phones, our calculators, the computers and stuff like that. They're all around us all the time. And all of these are essentially controlled electrochemical experiments. So along the way in this chapter, we're going to look at what a battery is, how to tell if the reaction is going to go or not, and also, probably more importantly, how to make reactions occur that wouldn't occur normally, all right? Electricity is a really interesting kind of force. So electrochemistry is nothing more than adding electricity or the study of electricity to chemical reactions. And even if my beloved DeltaG gives you a positive number, it might be possible to add some electricity and make the impossible possible. Oh, that sounds like a motivational speaker. Anyway, questions? Prophet, back on. Good. Most of the reactions in chemistry involve atom or groups of atoms being transferred from one species to another. And this is an example of a Ka expression, all right, that we talked about earlier. We have the weak acid acetic acid reacting with water, and for the amount of it that occurs, which isn't a lot, the hydrogen ion is transferred to water to make hydronium, and the acetate ion is the other product. So this would be an example of one atom being transferred. The hydrogen goes from the acid to the base in this case to make conjugate acid, and that's very, very common. But there's another type of reaction, and we started talking about it in Chem 221, but only briefly. And it was when electrons get transferred from one species to the other. And this is an example of an electron transfer reaction. The copper atom and the silver plus atom, when they come close to each other, there's a desire, if you will, for copper to transfer electrons to the silver ions. And you end up making copper 2 plus ions and silver metal. This is actually a really useful reaction if you're trying to claim silver metal from a solution of silver. Copper is often, although not always, cheaper than silver. So if you put a piece of copper metal in with your silver solution, the silver metal, which is what this is, begins to precipitate out, and you can sell it and make money. Anyway. Prophet on, I don't know why, I think my prophet fell off there, I'm going to put it back on. Anyway, this is an example now of electrons being transferred. And notice here how copper went from a 0 charge to a copper with a positive 2 charge. So copper here has lost electrons in order to make copper 2 plus. How many protons does neutral copper have? Good, you're looking at the periodic table? Serge? Yeah, good. 29. Good, I heard it there somewhere, I think. Anyway, 29 on the periodic table. That's the atomic number, all right? Yeah, good. Daria was helping him out there. Yeah, so the periodic tables, those atomic numbers, the 29 for Cu and silver is like 47. Yeah, those are the number of protons, all right? So copper here has 29 protons, and if it's neutral, it's going to have 29 electrons as well. Now on this side, you can see it's got a positive 2 charge. Copper still has 29 protons. If you change that number, you change copper into zinc or something like that. That's a nuclear reaction. That's harder to do. This still has 29 protons, but if it has a positive 2 charge, this thing only has 27 electrons. It has fewer negative ones than it had before. So we would say here that copper has lost 2 electrons to become copper 2 plus. The charge is the number of electrons, in this case, that copper is lost. Now silver, whether it's silver plus or silver metal, silver has 47 protons. And over here on the right side, if it's neutral, there's no positive or negative, that means that silver here has 47 protons and 47 electrons. The proton to electron mix is equal, so there's no charge. This version of silver has only 46 electrons, one less, all right? That's what a positive charge means. It has fewer electrons relative to the protons. So the silver plus here has gained an electron to become silver metal. It went from something positive to something neutral. And because electrons are negative, if you add one electron, it makes one silver plus neutral. On the other hand, copper here went to copper 2 plus. This copper lost 2 electrons. So in this problem, copper lost 2 electrons and it gave them to the silver plus. You need 2 silver pluses because each silver can only handle one more electron here. So you have 2 silver pluses becoming 2 silvers. This is an electron transfer reaction. The charges are critical. If you are a person that has been writing your charges on ions and stuff, you must start doing it in this section, all right? If you don't write the charges, then you won't know if you have copper or copper 2 plus or silver plus or silver. So please, 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 in this section, make sure you write all the charges down. So, any questions? In an electron transfer reaction, something is losing electrons, which we would say here is the copper, and something is gaining electrons, which here we would say is the silver plus. So notice that losing electrons means that electrons are products, and gaining electrons means that electrons are reactants. So this is why this reaction is an electron transfer reaction. You can't have electrons be lost and just have them go into space, and you can't have electrons be gained without a source of electrons. Both of these are needed. That's why this is another kind of yin-yang kind of symbol, like acids and bases, man, because you have to have a source of the electrons and you have to have a place to put the electrons too. You don't have to dig yin-yang, but it is kind of a cool thing in my world to think about. All right, prop that back on. Questions? Good. Now, the fancy name for these kind of reactions, which we talked about in Chem 221, are oxidation reduction reactions, or abbreviated for hopefully obvious cases, redox. And these are totally fine. And all of these redox reactions, because electrons are being transferred, it really comes down to a type of a current. So right here down by my feet is an electrical outlet. If you plug your phone into it or your computer or whatever, electricity is literally coming from that outlet to your computer or your phone. And electricity, for our purposes, is nothing more than little electrons being transferred. Electrons in motion, all right? And we're going to talk more about that. So these redox reactions, if you control the reaction, you can actually create electricity. You can actually create current, and you can measure it, and you can make your phone. If you go on YouTube, there's all these people like charging their phone with an orange or something like that, right? And it's totally quirky and stuff, but it's also kind of fun. This is what they're doing. They're controlling the current created in a reaction to make these things happen, which is really cool. So electrochemistry is just controlling these redox reactions so that you can create a type of a current. So you can use an orange to charge your phone or whatever your kind of thing is. This is like MacGyver kind of thing. If this is your, if you don't know MacGyver, don't worry about it. I don't know if I should even mention that. But anyway, all these kind of wacky things and stuff that people can do, a lot of it comes from the knowledge of electrochemistry, which is kind of cool. Okay. What's oxidation anyway? Gee, I don't know. My science is a little rusty. Boom, boom. So rust is a form of redox. It's iron going to iron 3 oxide. It is a type of an oxidation. So that's why this is really funny, because oxidation itself is a type of a rust forming process. So hopefully you see the humor in this incredibly cheesy experience. In Chem 221, we talked about these terms: oxidation, reduction, oxidizing agent, and reducing agent. Oxidizing means that something has lost electrons. Reduction means that something has gained electrons. So in the last example, the copper had lost electrons. It was the source of the oxidation. And the silver pluses were taking the electrons to make silver. Those would be the site of the reduction. But unfortunately in this segment, you have to think about the agent terms. And this is just a product of having a really old science with lots of different people working on it. An oxidizing agent is something that's been reduced. So if you hear about an oxidizing agent, that means that that species has been reduced. It isn't oxidized, it's reduced. And a reducing agent is allowing something else to be oxidized. So the oxidized species is also known as a reducing agent. I don't like these terms, but it is something that you run into a lot when you talk about people with electrochemistry. Any questions on this? All right, have a wonderful day. I'll see you guys in lab or in Wednesday.